Welcome back to the Enclosure Institute. I'm Jimmy Budd.
And I'm Phil Taylor. Today we're going to discuss some of the conditions that can cause degradation of the polymers of foam materials that are used in gasket applications.
We'll talk a little bit about the chemistry involved, and we'll explain some of the actual applications where these breakdowns may occur.
It's probably a statement of the obvious to say that as a polymer of a given gasket degrades, it will surely weaken the gasket's ability to maintain an effective seal.
But polymer degradation most often takes time. It doesn't happen overnight. So maybe the first question to ask yourself or your team is, what is the expected useful life of the device that you're trying to seal? Making the distinction between short-term, long-term, or something in between will help you decide whether polymer degradation is worth concern.
At Marian, we don't over-science this question. We kind of think of product lifespans in this way. If you measure the useful life of your device in hours, days, or weeks, then it's a short-term application. If you measure it in months, then it's probably medium-term. But if you measure it in years, we consider that long-term application.
As we've said before, many gasket materials will seal well on day one, but understanding how a material will hold up over time in challenging conditions could help you to make the best choice for the expected life of your product.
Today we'll discuss three common environmental conditions that can have a negative effect on the polymers of foam materials: oxidation, hydrolysis, and UV or ozone. Let's start with oxidation. The term oxidize describes a common or natural chemical reaction that is happening all around us. It's the reason my old bicycle is covered in rust and the reason my apple slices that I cut for breakfast turn brown before lunch.
To be oxidized means that a substance has experienced a chemical change from its interaction with oxygen and other conditions such as heat. Oxidation in foam gasket materials occurs when polymers react with heat and oxygen, leading to what is called a chain scission. A chain scission is a breakdown of the polymer's backbone. This causes the foam to become brittle and harder. Long-term, it can develop surface cracks and could eventually crack completely. Materials with unsaturated bonds like EPDM and nitrile are more prone to oxidation.
According to the publication Science Direct, polymers that are particularly susceptible to the negative effects of oxidation include polyethylene, polypropylene, and polyvinyl chloride, or PVC.
As oxidation of the gasket material progresses, it will accelerate stress relaxation and compression set. If your device and gasket are subject to the environment where oxidation flourishes, and your device is intended to function for a medium or long term, you will want to choose a material that is less susceptible to that chemical breakdown. For example, this would be true in high heat environments, like lighting enclosures and power inverters, where the performance of the gasket is critical to the long-term function of the enclosure it protects.
Now let's talk about hydrolysis, another harsh condition that works to degrade gasket materials.
Like oxidation, hydrolysis is also a chemical reaction. But in hydrolysis, the compound is broken down by reacting with water and/or humidity. This chemical reaction involves the addition of water molecules that break the chemical bonds in the polymer. In such conditions, the polymer will soften, become tacky, and over time, lose much or all of its mechanical strength. And as you may have guessed, experience stress relaxation and compression set.
Typically, natural rubber, butyl rubber, nylon, and some polyester urethanes are most susceptible to the ill effects of hydrolysis. However, certain formulations of pour-on urethane foams are engineered to be highly resistant to hydrolysis, making them well suited for environments where moisture exposure is common.
There are many applications for devices installed in very humid or moisture cycling environments. An example is telecom equipment mounted high on towers that are subject to rain or ocean salt spray, or meters and controllers installed in wet basements or underground tunnels. When your device and gasket must perform for the long term in such environments, you'll want to design with a polymer that is less likely to suffer from the degradation caused by hydrolysis. These include ether-based polyurethanes, silicones, or at least a neoprene or EPDM polymer that has added stabilizers to fight the chemical breakdown caused by humidity, moisture, and water.
Now let's discuss UV and ozone degradation. Ultraviolet radiation breaks the carbon-to-carbon bonds in polymers such as polyethylene and ethyl vinyl acetate or EVA foams. Polymers like neoprene and nitrile also degrade quickly unless UV stabilizers are added to the compound during curing processes. In time, UV exposure leads to surface cracking, chalking, brittleness, and that leads, no surprise, to accelerated stress relaxation and compression set.
If your device and gasket will be used outdoors, installed on rooftops as a part of exterior signage or any other application where prolonged exposure to the sun is involved, you should design with a material rated highly for UV resistance. Imagine a gasket in an aluminum frame exposed to midday sun and midnight frost. The seal must flex and rebound through thermal expansion cycles while resisting UV damage year-round. Silicone polymers will provide the longest lasting performance, and some microcellular urethanes do quite well.
Although often overlooked or lumped together with UV degradation, ozone, like ultraviolet light, reacts negatively with double bonds in elastomeric chains, causing surface cracks and reduction in tensile strength. Ozone occurs in industrial environments with high voltage equipment or electric discharge. Your choice of the polymer should follow the same guidelines as Jimmy just discussed for UV exposure.
Before we close our discussion on polymer degradation, let's briefly review some of the ways that you can compare materials or build expectations for long-term performance. As we mentioned earlier, if your device is only expected to perform for a short time, hours, days, or weeks, oxidation, hydrolysis, and UV exposure may not have enough time to cause a breakdown or a failure in your seal. But if you intend for functionality to be sustained for a medium or long period of time, then you'll want to know what you can expect from the material you choose. There are a few tests that can be used to build these expectations and to be able to compare materials when tested and when results are published.
The ASTM tests G154 and D573 simulate long-term outdoor exposure to UV and exposure to elevated temperatures.
ASTM D471 is a test that predicts how a material will resist common fluids like oils and solvents.
For measuring stress relaxation, that is, measuring the loss of sealing force over time under constant compression, ASTM D6147 and the ISO test 3384 are good predictors.
And ASTM D395 measures for compression set. As we've explained previously, C-set is the permanent deformation of the foam under load. Compression set is often accelerated at higher temperatures, which can speed up seal degradation in heat-intensive environments like engine compartments or power electronics.
Okay, Jimmy, that's enough for one day. We've given our viewers enough to mull over, so I'd say the mulling's over.
If you say so, Phil. Next time, we'll get into some design considerations for the sealing gap and how that affects the seal thickness, compression, and CFD. So until then, I'm Jimmy Budd.
And I'm Phil Taylor. See you next time.